We have already studied oscillations, so now it is time for us to study wave motion. This actually takes 3 chapters. This is our first chapter, chapter 16, wave motion. First of all, we all have heard about waves, and I'm sure you have heard about things called electromagnetic wave and mechanical waves. We'll look at the differences. But first, let's look at some general idea about what a wave is. We know what an oscillation is. For example, if I have a pendulum and I pull the bob to one side, let go of it, it's going to start to oscillate, right? In this case, there is only one oscillator, and that's the pendulum itself. And what if I have a whole bunch of oscillators, a whole bunch of single pendulum? They're all disconnected from each other though. Each of them can oscillate back and forth, but their oscillations are not linked to one another. Okay, what if I put in a connection between them? Okay, for example, I put a spring between each neighboring pair of these simple harmonic oscillators, and if I pull one of them, for example, and let go of it, of course this guy is going to start to swing, right? And that's going to cause the spring to compress or decompress, so that there will be a force on the spring which will be felt on the next one. So the next one will start to oscillate, which will in turn cause this spring to get compressed or decompressed, and that's going to trigger the oscillation of the next one, and the next one, and the next one. Okay, so what you have here is a collection of oscillators, not just in this case like a single oscillator. You have a whole bunch of these oscillators. Okay, we have this collection of oscillators, and we give it a name. We call it a medium. Okay, a medium. You know, a medium can be air, water, whatever. In this case, the medium is a whole bunch of oscillators. Okay, and when we introduce a mechanism to connect these particles of the media together, like in this case, it's actually a spring connecting these two oscillators together, and then when I start a disturbance on certain part of the medium, say here on the left side, then because these oscillators are interconnected, the disturbance starting from here will be felt at the next oscillator, next, and so on and so forth. So in other words, you have a propagation of oscillation from one side of the medium down to the other side. Okay, so you have a medium which consists of a whole bunch of oscillators, and you have a connection mechanism between particles of the medium, and then if you start a disturbance on one part of the medium, the disturbance can propagate. This, we say, is a wave. So exactly what is a wave? It is the propagation of oscillation through a medium. Okay. First of all, you need a source to start the oscillation, or in general, disturbance. You need a source of disturbance, and then you need a medium, which is a collection of oscillators, and it must be able to propagate through that medium, which means different parts of the media, or the different particles in the medium, must be interconnected. Like in the previous case, we used a spring to do so. Okay, so again, what is a wave? It is a propagation of oscillation through a medium. Why is wave so important? Well, among other things, one unique thing about a wave is that it allows for energy to propagate, to transfer, okay? Not matter. Oftentimes, energy and matter move together. For example, if an electron is shot from one side to another, not only does it bring energy, it also actually brings this physical particle, the electron. But a wave is different. When you have oscillation, for example, let's bring back this case. Okay, you have oscillation of these particles. Of course, when this thing starts to oscillate, it starts to have energy, have mechanical energy. You start from this oscillator, then the wave propagates to the next one, to the next one, to the next one, to the next one. Even though energy propagates this way, the actual pendulum, this pendulum never actually makes its way over there, does it? It stays here, right? It can always oscillate back and forth. It never actually jumps from here to there. So you know, wave is a way for energy to propagate without carrying physical particles with it. So this is an important mechanism. Okay, there are different types of waves depending on how you classify them. You can classify them according to the physical origin. So for example, is this a mechanical or electromagnetic? We're going to study electromagnetic waves in detail in Physics 1C. What is a mechanical wave? Well, a mechanical wave allows for mechanical oscillation. So you say, for example, you have a particle of the air, okay, say an air molecule, oscillating up and down or left and right due to a wave that propagates through it. In fact, if the frequency of that wave is right, we can actually hear it because this is called sound wave. Okay, so a mechanical oscillation propagating through a medium is called a mechanical wave. Okay, why is wave so important? Well, I have here a short list of examples, just to give you an idea why waves are so important. In fact, wave is such a widespread phenomenon. You see it everywhere around us in the physical world. For example, light. How do we see things? Okay, how does the light from the sun reach us? Well, light is actually a form of electromagnetic wave, as we will learn in Physics 1C. Without wave, there won't be any light. We cannot see anything, and the light of the sun cannot reach us. Okay, the details will be studied later, but let me just tell you, this is a form of wave, even though it's not mechanical wave. Sound. Okay, now we use light to see things, we use the sound to hear things. Sound is not only a wave, it's actually a mechanical wave, which we'll be studying in this chapter, starting from this chapter. In the case of sound, you have, for example, air, in which sound can propagate. The air molecules can actually oscillate back and forth in response to a certain disturbance, and that oscillation can travel through the air. It can go from one part of the air to another. It can reach your eardrums, causing our eardrum to vibrate, and that's how we hear things. Okay, so that's another important example of waves, sound wave. Without a sound wave, of course, we cannot hear anything. In general, waves are important because they allow energy and or information to propagate, to transfer. Speaking of energy transfer, how does the energy from the sun reach us? Now, we feel the warmth of the sun, right? Without the energy from the sun, nothing can survive on this planet. How does the energy of the sun reach us? Well, it travels through this vast empty space through a mechanism called the electromagnetic wave. Okay, so you can easily understand why wave is so important. What about information? When you use telephone service, when you talk to people on the cell phone, and so on, have you ever wondered how does the information get through? Okay, the way telecommunications work, whether it's a telephone or internet service, whatever you think of, is by using a wave as well. And it's actually also electromagnetic wave. So without wave, energy and information will have a hard time going through, and therefore waves are incredibly important. Speaking of the importance of wave, just like any other physical phenomena, there are sometimes good things, sometimes bad things when it comes to waves. Earthquakes and tsunamis, these are destructive natural phenomena that also utilize waves. In the case of an earthquake, you have part of the earth shaking up and down, and that causes a wave to propagate. The speed of that wave depends on the nature of the wave itself. It depends on the properties of the earth around, of the region of the earth around it, and so forth. And tsunami, of course, is a very big recent phenomenon. How does tsunami happen? Well, it usually starts with an earthquake. You have an earthquake that shakes the seabed, right? And that rocks the water and causes the water to oscillate up and down in a certain region. And that oscillation will propagate in the form of a wave, which travels pretty fast. And how does tsunami cause such great devastation? Well, that actually has to do with the speed of the tsunami wave, which depends on the depth of the water. In general, when wave propagates in water, its speed depends on the depth of the water, and as the wave nears the seashore, the shoreline, of course, the depth of the water decreases, and that generally decreases the speed of the water. So you can imagine a wavefront of tsunami coming from the ocean, and it slows down because as it approaches the beach, it slows down, right? But the next wave of the tsunami came from deeper ocean, so they're still going pretty fast. So this is just like a pileup of a traffic bottleneck, right? You have you have an accident, everybody slows down, and so if you approach that accident scene, what you have to do is you have to step on the brake and slow down, right? Now imagine if the water, wave as a as a car, and it doesn't have a good brake. What happens? It piles up, right? It has no place to go but up. So the tsunami wave can rise dramatically to several stories, and it crashes ashore. It can wipe out everything. So that is just a devastating example of mechanical waves. You have so many examples. The wave phenomena is one of the most common phenomena in nature. It will exist in every single branch of physics. We're just beginning to study this very, very important situation in physics. So let's concentrate on the study of waves. There are different ways to classify waves, and one of the ways to classify waves is to look at the direction of the propagation of waves. Say a wave propagates down this way, versus the direction of the oscillation of the medium particles inside the wave. For example, if a particle oscillates back and forth, if every particle oscillates back and forth in this direction, yet the wave propagates down in that direction, and there is an angle of 90 degrees between them, then this type of wave has a special name. We call it a transverse wave. Okay, let's look at an example of a transverse wave. Suppose I have a rope. One end of the rope is attached to a wall, and the other end is free. And if I wiggle one end of the rope like this, okay, I grab the rope like this and I wiggle it. My hand moves up and down, and yet the rope is horizontal. You know, when you do so, the wave will propagate along the rope, so the propagation direction of the rope is horizontal, yet my hand moves vertically, so there is a wave going, there is an oscillation going up and down in a vertical direction. If you look at each particle, let's say this particle P in the wave. Okay, this particle P right now is here, next moment it goes up, and then it starts to go down, and so forth. So this particle goes up and down, yet the wave propagates from left to right. The propagation direction is horizontal, the oscillation of any medium particle is vertical, and they make 90 degrees from each other. So this is an example of a transverse wave. Now, also please pay attention to this fact, and that is, if you look at a typical medium particle, which is point P, this particle can only move up and down in this case. It never actually moves along the direction of the wave. It never actually moves from the hand, for example, to the end of the wall. Okay, it is only this oscillation pattern that travels from my hand to the wall and actually can even bounce back, but not any medium particle. Okay, so you see, just like we said, it is a way for energy to propagate without moving particles along with it. Okay, another example, another type of wave is what's called longitudinal wave, and an example would be wave in a long spring. All right, you have a spring in a horizontal direction. Now, you take this end of the spring and you pull it horizontally, okay? You pull it horizontally and you go back and forth. In doing so, of course, you're going to send a wave down. Now, look at each ring, okay, or each segment in that spring. This acts like a particle in a medium, and what it does, it goes back and forth, right? Causing part of the spring to get compressed, and this part of the spring to get stretched, and this part of the spring is stretched, this part is compressed, and so on, due to the different movement of each segment. And since each segment this time moves horizontally, while the wave propagates down the spring also horizontally. Okay, so the moving direction of the medium particle and the propagation direction of the wave this time lies on the same line, And this particular situation is what's called a longitudinal wave. Okay, these are two very common types of waves, transverse and longitudinal. But let me emphasize on one thing, and that is a wave does not have to be either transverse or longitudinal. It does not have to be, okay? Because the propagation direction and oscillation direction, the angle between them can be in general anything. It doesn't have to be either 0 degrees or 90 degrees. We're going to study both transverse and longitudinal waves in detail. In particular, as we will learn, sound wave is actually a longitudinal wave, so we'll be studying sound wave in a separate chapter. And a transverse wave, there are many examples of transverse wave. Electromagnetic wave is perhaps the most important transverse wave. But we're going to focus primarily on mechanical wave, and in particular, we're going to use the wave on a string to demonstrate properties of transverse wave. Okay, we're now going to discuss the so-called wave equation, using a wave on a string as an example. The derivation of the wave equation not only tells us how Newton's second law can actually be used to study the wave on a string, it also gives us this important wave equation which is valid not only for this type of wave on a string but for general type of wave. So it is an important discussion. Let's say we have a string which is in red in this case. Okay, it is otherwise flat, and let's ignore gravitational effect so that only the tension in the string should be considered. Now, what if I hold on to the free end of the string and I give it one single wiggle, just for simplicity, just one single wiggle? I'm going to cause a hump, right? And this hump then will travel along the string at a certain speed. Okay, common sense tells us that if the string is highly elastic, then this hump will keep on its form for quite some time before it actually decays back to zero. So let us look at the simple idea. Suppose I have this wave pattern, like in this case it's just a single hump. It doesn't have to be, but that would be the simpler case to discuss. And it travels with a certain speed v, undiminished. Okay? Keeps on going, keeps on going, keeps on going. It does not change its shape or size. How does one describe mathematically this type of motion? Well, if I take a snapshot of the wave, okay, this is the x-coordinate. This basically tells you where on the string a certain particle of oscillation is. Okay, so a certain x value tells you which part of the string we're talking about. Okay, and I have here a y-axis. Y is the displacement of the wave pattern. For example, from at this point, okay, at this point, the string is originally here, but due to the wave, oscillation actually moves up to there. That distance is y at that point. Now, in general, as the wave propagates down the string, y, the displacement of the wave from its original position, is a function of both the location and the time. All right? So we're looking for y as a function of both x and t. Okay, the question is, how do we find that? Well, before we apply Newton's second law to solve this problem, let's observe one thing. If the wave pattern propagates down the string undiminished, in other words, does not change its shape and size, it propagates with a speed v without changing the shape and size. Can we say something general about this function? Well, actually, we can. Let's take a look at what happens at t equal to 0. We choose an arbitrary time t equal to 0, and that moment we have a camera and we take a snapshot. Okay, this is the snapshot. X coordinate, y coordinate, and I have this function, right? This function is y at x and 0. Y 0 because t is equal to 0. Okay? Now, that function, whatever it is a function f of x, right? It doesn't have dependency on t because t is set to be 0. It's not a variable. Okay, this f of x is any reasonable smooth function. Now, what happens at time t later? At a time t later, the wave propagated from here to there. It moved a distance down the string. What is that distance? V times t, of course. V is the speed of the wave, right? So after time t, that's how far it propagates. The wave pattern propagates by a distance of v times t. Okay, now, if we look at these 2 points, okay, look at these 2 points. these 2 points are apart from each other by a distance v times t. And what can we say about the oscillation at these 2 points? Well, at this point, I have this much oscillation, right? At that point, what do I have? I have the same exact amount of oscillation. Why? Because these 2 points are the 2 corresponding points in these 2 humps. And since the shape does not change from here to there, this displacement equals that displacement. All right, so what that tells us is that there exists a connection between the waveform here and there. In particular, at time t, later we should look at, let's extend the x-axis, okay? We're looking for this wave, right? This is the wave that I get at this moment, right? Not the wave at t equal to 0, right? Now, at this point, okay, this is our new distance, x, right? At that new distance, the waveform is y of x and t, right? This is x, and time is t, right? How is that related to the old pattern? Well, we know y of x and t is this height, right? It equals that height, right? But what exactly is that height? Well, that height is f at what location now? Remember, this is our x now, right? We're looking for that, right? That's the argument, right? This is x, and what's that? That's vt. So isn't this equal to x minus vt? Right? So what did that tell us? It tells us that if we know the function which describes this waveform at t equal to 0, we call this function f of x. So again, what is f of x? It is the form of the wave at t equal to 0. Then, if the wave propagates down the string with a speed v, undiminished, okay, the pattern does not change, then I can find the wave displacement y at any location x at any time t later. All I have to do is to take that f, same exact function f, and shift x to x minus vt. That is all I have to do, okay, because I utilize the fact that this displacement equals that displacement. So this is fairly general description mathematically for this wave. I did not really restrict the form f. F can be any reasonable smooth function which can describe a wave. Now this is interesting because we are dealing with a very, very general smooth function here. We're not dealing with a specific function like sine or cosine, right? Now we learned that a simple harmonic motion, which is a sine or cosine function of time, requires a specific type of force, which is linear restoring force. Okay, so if you give me a linear restoring force, the motion has got to be simple harmonic, sine or cosine, cannot be anything else, cannot be exponential or whatever, right? Here, however, the wave, this is the solution to the wave equation, right? It's, it's not the equation itself, it's actually the final solution itself. Yet it has a very general function, f. It is not necessarily sine, not necessarily cosine, whatever. So the thing is, how does one find an equation whose solution will look like this? This got to be a very interesting equation because I don't think we have had an equation before whose solution would be just pretty much any smooth, reasonable function, right? Here we'll derive a wave equation, okay, whose solution can be very, very general. It is not restricted to sine, cosine, whatever. It is any reasonable smooth function as long as x and t appears in this combination. This is a first for us. Okay, it is not only interesting, but it's also good because what that means is that whatever equation that we get, the solution being so general, it can describe so many different types of waves, not just sine or cosine. In other words, not just sinusoidal waves. All right, so what kind of equation can we obtain? Well, this calls for Newton's second law. We want to study the wave motion with Newton's second law. Newton's second law basically says F equals ma, right? You can apply that to, a whole object or to a segment, whatever. Now, in our case, do you think it's a good idea to apply Newton's second law to the entire string? Probably not, because remember, every different part will have different motion, right? Different displacement, different velocity, different acceleration, and so forth, right? you're dealing with a non-uniform situation. And in math, when you have a non-uniform situation to deal with, what do? Well, one important weapon is calculus, and that is what you do. You cut a little piece out, right? Let me isolate this little piece out, and let's apply Newton's second only to this little piece. Since the piece is so little from here to there, we say the acceleration from here to there pretty much is the same, whether it's this point, or this point. Okay, so let us isolate a certain segment of the string out and try to apply Newton's second law to this segment and see what happens.